Good morning and good afternoon, everyone, and welcome to the second set of webinars on the International Forum on Research and Development around Marine Renewable Energy Effects. This is Andrea Copping with Pacific Northwest National Laboratory in the U.S., representing Ocean Energy Systems Environmental. And my co-host here today is Jennifer Fox with Aquaterra, representing Ocean Energy ORJIP. Many of you were with us yesterday, and I don't want to bore you with this again, but just a quick once-over for those who are new. Ocean Energy Systems is one of the International Energy Agency groups of countries that come together to promote the use, the responsible use of marine energy as a power source. And one of those tasks, OES-Environmental, consists of 15 nations that are coming together specifically around environmental effects understanding as they affect consenting or permitting. This particular task is led by the U.S. Department of Energy as the lead, with the Bureau of Ocean Energy Management and the National Oceanic and Atmospheric Administration as well. We have been running this for about 10 years in 4-year phases, and we are honored as Pacific Northwest National Lab to get to implement it. And this next phase is ending just in another month with the release of the State of the Science report, which will be an update to one done in 2016. And so I hope you'll all look forward to that. So Jen, do you want to go ahead?
Thanks, Andrea. So many of you might have been on the call with us yesterday, but for anyone who wasn't, just to introduce ORJIP, Ocean Energy. It's a UK-wide collaborative program aimed at reducing the uncertainty around the environmental effects of wave and tidal energy. We are funded through 6 different public bodies within the UK, and we as Aquaterra run the Secretariat for ORJIP Ocean Energy, along with 2 other organizations called Marine Space and the European Marine Energy Centre, or EMEC. And through ORJIP, what we aim to do is to facilitate a strategic, coordinated and prioritized approach to the monitoring and research around wave and tidal energy projects. And one of the main ways that we do that is through the Forward Look document, which we've produced a number of iterations of over the years. And that is essentially a prioritized list of the key consenting risks and research goals for the environmental effects of wave and tidal energy. We're working towards a new version of the Forward Look, which will be coming out in the coming months as well.
Thanks, Jen. Okay, so again, many of you saw this yesterday, but what is the purpose of what we're doing? We are trying to put together this recurring forum internationally that will showcase our up-to-date R&D around environmental effects, demonstrate what monitoring techniques and technology are being used, and most of these are developed through research programs, although then the purpose is to be able to deploy these on an ongoing basis around existing projects. This should also introduce many of you to lead researchers and monitoring people in this area. And although you're hearing in these 3 days a lot of presentations, in future we'd like to have more time to really understand people's questions, comments, uncertainties, to really kind of try to build this kind of community further. We were fortunate enough yesterday to have a really good set of presentations on monitoring research around turbines. And for your information, that has been recorded and it will go up on the TIFAS webpage sometime in the next week or 2. We have 2 more days today, starting with integrated monitoring platforms, a great lineup. And there's a 3rd webinar tomorrow that will focus around wave devices.
Thanks, Andrea. So today we've got 4 speakers. As Andrea said, we're going to be focusing on the design and implementation of integrated monitoring platforms for monitoring around marine renewable energy devices. So the first of our speakers is James Jocelyn at the University of Washington, talking about the Adaptable Monitoring Platform, or AMP. Secondly, we have Benjamin Williamson and Beth Scott from the University of Aberdeen talking about the FlowBEC platform. And thirdly, we've got Gordon Hasty and Doug Gillespie from the Sea Mammal Research Unit talking about the SMRU platform. And finally, we'll have Dan Hasselman from the Fundy Ocean Research Center for Energy talking about the FAST platform.
Okay, with that, I think we're going to turn it over to our first speaker, James Jocelyn.
Thanks for the introduction. My name is James Joslin, and I am with the University of Washington. And the project that I'm going to be presenting to you today is on the Adaptable Monitoring Package, or what we call the AMP. And this has been a system that has been under development by the Pacific Marine Energy Center at the University of Washington since about 2011, so about 9 years now. And really, there are far too many people to thank and acknowledge that have contributed to this project that I could ever list in the presentation. But this is the core team that is currently working on this at the University of Washington. And just to give you a little bit of background, let me figure out how to advance the slide. As you all are aware, I'm sure the primary motivation for developing environmental monitoring packages is to try to assess the interactions between things like tidal turbines and marine mammals. And there are a lot of challenges to operating in these types of environments, particularly that these are typically in areas that are extremely high energy and are places that you wouldn't really normally want to go and put instrumentation, because most instrumentation is not designed to survive in these types of environments. The type of sensors that you need for this to do this type of monitoring also requires a lot of different things to collect the information that you really need to understand what's happening. And finally, the events that we're looking for, if they happen at all, are probably going to be extremely rare. And so in developing this system, we've really been following a set of monitoring directives that we came up with that basically say that you should avoid biasing marine life in doing the monitoring itself, because if you do that, you're basically just going to be monitoring yourself, and you're not going to actually understand the difference between what are environmental effects from the device you're monitoring versus your own lights, per se. And second is that you should be able to detect these rare events, which means that you need to be monitoring basically continuously to avoid missing them. And third, the final directive is that in doing this, you shouldn't accrue so much data that you can't actually process it, which is what we call a data mortgage. And so this is the most recent version of the Adaptable Monitoring Package. It's basically an integrated instrumentation suite into a single body that contains a Nortex signature ADCP, the Tritech Gemini multi-beam sonar, a Blueview multi-beam sonar, 2 optical cameras for stereo vision, 4 sets of strobe lights that are both red and white LEDs, a Simrad WBT Mini Echo Sounder, 4 IC Listen hydrophones, an Seaward EcoBB water clarity sensor, the Vemco VR2C cabled fish tag monitor or receiver, ROS rotator to turn the instrument head that has all the instruments in the field of view, and then a recovery float with an autonomous acoustic release. And this is all built onto, in this figure, a very low-profile tripod lander that can be deployed on the bottom. And so just to go over the system architecture, we basically, the main backbone of the AMP is the integration hub that has a power supply, and then a suite of sensors that all plug into a single instrumentation hub bottle. And then that connects to a computer that is typically on shore, but not necessarily. And the computer is running the instrument control and data acquisition on all of the sensors. And those sensors are basically running continuously and storing the data in temporary ring buffers. And then we have real-time data processing modules that are looking at the data that is coming in and performing target tracking and classification. And of the system, everything that is above the dotted line here, we can generally consider deployment agnostic, and something that we would include on any deployment, while everything below the line, it could be deployment specific. So you basically could tailor the instrument suite you want depending on the environmental monitoring goals and the conditions where you are deploying it. So to go through all of the deployments we've done to date, or most of them anyway, in 2017 we deployed the prototype version of the AMP that we called the IAMP, and we did this in Squim Bay, Washington, off of the Pacific Northwest National Laboratory Marine Science Lab. And it was in the water for about 2.5 months, during which time we had 94% operational time. And we were able to implement the initial version of the sonar, multi-beam sonar to target detection and tracking. Also in 2017, in the summer, we deployed an autonomous version of the system, which basically took that computer and put it in a bottle and operated off of a battery bank off the coast of Oregon at what is now the Pathways site for about a month and a half. And during this deployment, we were basically only doing triggering off of the VEMCO fish tag monitor. In 2018-19, we worked with the University of Hawaii and Fred Olsen out of Norway to integrate a version of our system on the Fred Olsen Lifesaver wave energy converter. And this was a fully autonomous deployment where we received all of our power from the Lifesaver and then transmitted all of our data to shore via a radio link. And during this deployment, we were operational for about 3.5 months with over 82% uptime, which is pretty good considering that we had no connection to the grid. And we were able to do real-time target detection and tracking on the multi-beam sonars again. Then this last year, in 2019, we did a subsequent deployment of what we're calling the third generation AMP, or 3G AMP, back in Squim Bay. And this was a 4-month deployment where we implemented target detection tracking as well as classification and had over 96% uptime. And currently, we have a couple of different projects that are still ongoing. One is to implement the 3G AMP on the OE-35 wave energy converter back out in Hawaii at the wave energy test site. And this deployment should be approximately 12 months in duration, and we're hoping to have the multi-beam sonar target detection and classification as well as optical target detection and classification operating, looking down across the sea duct of the OE-35. We are also working on a small tidal turbine deployment that will be again in Squim Bay, Washington, with approximately a 1 square meter cross-section turbine, and doing several 6-month deployments with the AMP positioned to monitor interaction with the turbine as well as upstream and downstream. And to give you some examples of data that we've collected to date, these are co-registered images of this first one is a school of fish in the Blue View sonar as well as the optical cameras in Squim Bay. The second one here is a seal that is coming up and picking out the AMP. And the third one here is a diving seabird that swims into the field of view and across in front of the AMP. And this is a good demonstration of what we are really focused on today is all of the automated data processing and target detection. So here is a sequence of data from the deployment in Hawaii where we were underneath the Lifesaver wave energy converter. And you can see fish and different marine life tracked with the multi-beam sonar, the Blue View, as well as the optical camera. You can see everything basically boxed in blue boxes. And so, yeah, this is basically giving us the ability to automatically detect and tune out things that would otherwise basically cause false detections in the sonar and optical camera fields of view. And so, I guess, to go over a summary of the lessons learned over the last 9 years of this development, that integrated platforms offer new and exciting capabilities, but we shouldn't underestimate the complexity of sensor integration. It has taken us a lot of time and development to get all of these things to work well together. And in general, with these projects, we should be considering data collection objectives early and often. If you know what you're trying to look for, it's a lot easier to design the study to make sure that you are successful in the end. And as I said at the beginning, there are far too many people to really acknowledge in this presentation, but we would like to thank basically all of them, and in particular, this list here. Thank you very much.
We have one question that just came in as Benjamin gets set up. What are the power needs for the AMP, James?
Yeah, I see actually two questions in there. The power needs for the AMP during the Lifesaver deployment, that gave us the best estimate of that since we were drawing and monitoring all of our power from the Lifesaver. The instrumentation suite itself is about 180 watts for all of the different instruments, including the high power strobe lights, and which are really the main power hog. But then if you're also including the computer, and in that case, we had a pretty large power budget for cooling because we were in Hawaii, and putting a computer in a box, a sealed box in Hawaii is not really a good idea. But for that system, we typically were operating around 500 watts with everything included. And then I see from Tony asking if we have the automated image analysis, and the answer there is yes. We have recently implemented basically a deep learning algorithm to automatically pull out fish and classify basically the targets that you're looking for in the optical imagery.
Great. Thank you. Okay, I think we'll go on to the next presentation. Thank you, James. So, Benjamin, you have this one.
Perfect. So thank you for the introduction and the opportunity to present. Thank you, James, for some really useful context and background. My name is Benjamin Williamson. So today I'll be talking about how we developed and used the Flowback integrated monitoring platform. And then partway through, I'll hand over to my colleague, Beth Scott, and she'll finish by talking about some of the bigger picture considerations and integration with surveys. So I'd like to gratefully acknowledge the many funders of this work and the co-authors, and you'll hear about the work of some of the PhD students later on. So I'll start with some background on the Flowback platform. We developed it to provide detection, tracking, classification, and kinematic metrics across trophic levels, so measuring fish, bird, and mammal distribution, but also to measure animal behavior and predator-prey interactions. And this allows us to measure animal-turbine interactions, such as encounters and collision risk. But the unique way in which we orientate the sensors means we measure the entire water column. I'll show you a diagram on a later slide. And that lets us investigate vertical and horizontal evasion. We take measurements continuously across the spring tidal cycle, and we use acoustics, so we're irrespective of visibility and illumination. And crucially, we take concurrent physical explanatory measurements, and that allows us to measure biophysical interactions, but also allows us to look at the predictability and the transferability of results between sites. So with those requirements, we need concurrent information on hydrodynamics, animal distribution and identification, and animal behavior. So the core instrument suite of Flowback is simultaneous operation of an ADV and ADCP for flow measurement. We use a multi-frequency echo sounder for animal detection, and a multi-beam echo sounder for animal behavior. We also use a turbidimeter and a fluorometer for lower level oceanographic measurements. We trial the camera to aid with target identification for the limited daytime periods when visibility permits in the sites that we work in. And we trialed hydrophones to detect vocalizing marine mammals. But today we'll focus on the active acoustic core instruments, those top four. So on Flowback, we orientate the multi-frequency and multi-beam echo sounders vertically with overlapping beams. And so that means we can use the EK60 beam, which is in orange here in the center, to detect and discriminate targets with a high sensitivity and good robustness across flow speed. And then we can track the movement, behavior, and turbine interactions or evasion of the same target using this overlapping multi-beam swap, the semicircle here in blue. And so as you'll see from this Venn diagram at the bottom of the screen, overlapping the instruments in space and operating them concurrently in time allows us to combine the benefits of each system by co-registering targets. We all know these are very challenging sites to take measurements in, and so it's this co-registration that gives us robust detections, as well as being able to track the movements and behavior. And this is what the co-registered results look like. So for every target, we work through three different stages. First of all, at the top right, we use the EK60 on this right-hand side here for robust detection of targets, despite large amounts of turbulence and entrained air you can see up here near the surface. So the platform's down here on the seabed. The x-axis here is time. There's a school of fish detected, in and around the entrained air. Then the second step is for every target, we use the multi-beam echo sounder to track movement and behavior. And so in this case, on the left-hand side here, we're looking at a composite multi-beam image, and we're tracking that same school of fish as it swims away from the turbine structure you see down here on the seabed, from blue at the start of the track through to red at the end of the track. And then finally, we use target morphology, movement, and for fish schools, the frequency response using the multi-frequency echo sounder to aid in our classification. And so we can deploy the platform in two different configurations, either fully autonomous using onboard batteries and data storage. And so that's the image on the left-hand side of the screen. And this autonomous deployment lets you carry out baseline studies before a turbine is installed, or once a turbine is installed, you can move the platform around to look at controlled impact studies or the range of effect, the spatial range of effect of an array. And then the second deployment configuration is cabled to a turbine structure. So we've developed an interface that can be cabled in, and that gives you real-time feedback of data via a turbine export cable, and it increases the monitoring endurance as you then need to regularly service the platform to recharge batteries and to download data. So although we heard yesterday from Douglas about some of the difficulties Magen had in commissioning their turbine interface as a testament to the robustness of flowback after 21 months subsea, waiting for the turbine interface to be commissioned, flowback was recovered and still operational. So we're confident of the platform design and resilience in these sites using these two operating rates. And so these are the kind of results we can get from a deployment. There's a lot on this slide, so I'll just talk you through it step by step. But what we're doing here is we're comparing back-to-back measurements with and without a turbine structure. So we can show, first of all, that there's more fish around the turbine structure. And so that's going from this top right plot down to the bottom right plot. And what we're looking at here is the vertical distribution of fish schools swimming past the turbine structure with no turbine at the top and in the wake of the turbine at the bottom. So first of all, we see there's more schools, more fish, more prey around the turbine structure. We see the vertical distribution changes completely, but we're taking concurrent hydrodynamic measurements to better explain and predict why that's occurring. And then we also see many, many more fish in the low speed wake. So that's the blue bars down here on the bottom right-hand side. And so that's significant because we're taking considerations there about whether it's above or below a turbine cutting speed. And so considering these fish as prey, we can then investigate the effects of attraction and aggregation on the predators foraging in these sites and what that means positively and negatively for prey availability and collision risk. And so at that point, I'll hand over to Beth with the big responsibility of explaining why it's important. So thank you very much. Beth, can you hear us?
Yeah, I can. And so we're going to do this joint act where Benjamin gets to pick the slides. Okay, thank you. Hello, everybody, and thank you for this opportunity to explain how we feel integrated platforms should be used to answer the bigger picture about large-scale marine renewable impacts. Why we are so focused on measuring the physical features and the prey together, when everybody seems to know that consenting risks are mainly about top predator populations. Well, this is down to a lot of our wider ecological research, where we have shown links between physical habitat types and the ability to predict if these are foraging habitats for top predators. So we suggest that if we're right, and we can predict higher or lower times of the risk of collisions from either just the presence of prey or maybe just from the hydrodynamic characteristics. If this is indeed the case, then ultimately the cost of monitoring and the complexity of mitigation techniques could decrease substantially. Next slide. Yeah. I will briefly take you through what I mean on this slide. We start with the physical habitat, and what I'm showing here is an animation of the current strength and direction in the Pentland Firth in the area of the Magen deployment. Using these finer scale three-dimensional predictable models, we can start to look at which physical habitats we think are going to be the important foraging habitats for seabirds and mammals. In the bigger picture, we suggest first to use a vessel that is kitted out with the same type of acoustic instruments that we have on our upward-facing integrated platform, by now performing downward-facing surveys while also observing visible top predators. Of course, dealing with mobile animals, there is a lot of potential variation due to the time of day and season, etc., in their use of the site. So, of course, you need to do multiple surveys, and they should be done in at least contrasting seasons. Seasonal monitoring methods are already in use, of course, but the use of vessels with the proper acoustic instruments has hardly ever been used, and that's our main point, because you need to be measuring the physics and the prey and the top predators simultaneously, and be identifying areas, like we have in these boxes here, where you suspect are the foraging sites of a range of species. So what I'm showing here is a successful deployment location where we have the Flowbeck integrated platform running before the MyGen turbines went in 2015. The original plan was to deploy the platform in several of these contrasting foraging areas. However, eventually what we managed to get done is a pre- and post-deployment surveys in 2016 and 2018, working with Marine Scotland Science and the use of the vessel, the Scotia, which has all the proper instrumentation. So what you're seeing here in the pictures below are the distributions of black guillemots on the left and kittiwakes on the right in the before and after years. It's quite clear that for black guillemots, they have a pretty much the same distribution, but there's quite a change for the kittiwakes. Now, if we just follow the current protocols, we would have to do many, many more surveys to see if these changes in distributions have anything to do with the changes in the abundance of the local populations or the presence of the turbines. However, what we are suggesting is a different approach that involves identifying and predicting the preferred foraging habitats of seabirds and mammals. What we are currently doing with a range of PhDs, and then the first one I'll cover is by James Chapman, where he is investigating linking changes in habitat directly to predicting changes in populations using some sophisticated spatial modeling, and he has been analyzing the upward-facing platform data. With Anna Kuto, she is looking at the 2 years of Scotia survey data before and after, and being able to link the physics directly to the prey and the prey to the predator behaviors. And then with James Slingby, we also ran drones out in front of our survey, and he is using that information to try to understand better the links between the predator use of some of these very transient characteristics of the high energy sites, such as these boils. So of course I don't have time to go into the details here, but if you're interested in this work, all three of these PhDs are currently presenting their work online via the EMER 2020 conference. And you can either email the EMER site, or you can actually now, I think everything's up on the web, you can just Google EMER 2020 and go directly to these talks. So in conclusion, how we would recommend that integrating platforms are best used is to identify these predictable foraging habitats. And by measuring the physics and the prey and the predators simultaneously, we are going to be able to predict foraging locations in any high energy environment. Once we understand those links between the hydrodynamics and the foraging behavior of predators, we can have predictive power in what the physical changes that large-scale arrays will have on the location and quality of foraging areas. And that will eventually lead to the predictions of population-level changes of predators. Therefore, in the long run, we may only have to monitor some of the physical changes or maybe just the presence of the prey, and therefore we can evolve towards a low-cost but very effective monitoring system. Thank you.
My name is Gordon Hastie. I'm a researcher at the Sea Mammal Research Unit at the University of St Andrews. And I'm going to describe a development project very much from a biologist's perspective over the last couple of years. And from a technical perspective, this has been very much driven by some of my co-authors here, Douglas Gillespie and Mike Oswald at the Sea Mammal Research Unit, and Fraser Johnson at Atlantis. Now, equally, upfront projects like this are never done in isolation, so a massive thank you to all those who've helped along the way, both in terms of the funding steering groups from the Scottish Government, from the Natural Environment Research Council, and also in terms of technical support from the Sea Mammal Research Unit and elsewhere at the University of Aberdeen and Atlantis. So the overall aim of the project, very similar to the previous two talks, is to measure the movement of animals, and in this case marine mammals, in high resolution close to operational turbines. And this is done very much with a view to informing collision risk. And I'd also like to thank James and Benjamin for a wonderful introduction into some of the aims and challenges associated with monitoring animals in these environments. We've now collected marine mammal data around a number of demonstration turbines. And a couple of things to notice about these. First of all, each is very different in terms of its design. Secondly, each has relatively large foundation infrastructure. And the good thing about this is that it allowed us to attach various instruments relatively close to the turbine. But the bad thing is that each monitoring system we've had to develop has had to be fairly bespoke in design. And it's also unlikely that future turbines are going to have this level of foundation. So we were recently awarded Research Council funding to try and reduce the need for these highly bespoke systems and try and integrate the approaches we've been taking to detecting and tracking marine mammals into a common system. And we hope as far as possible to try and standardize some of the data collection and analysis systems we've been using. And perhaps most importantly, we hope to make as much of both the hardware and the software, as much of this as possible, open source. There's a relatively small number of technologies that can be used to reliably track marine mammal movements underwater at the kind of scales that we're interested in, so at scales of meters and seconds. And we've already heard about these already in this webinar. For the project, we're using, firstly, active acoustic techniques, multi-beam sonar. This has been used extensively to make measurements and geolocate marine mammals underwater. I know that from a Scottish marine mammal and turbine perspective, harbour seals are one of the key receptors, one of the key contenting risks at present. And this video you'll just have seen here was an image of a single adult harbour seal that we detected in a tidal environment over the last couple of years. And it's very much this species we've been focusing on in terms of the active acoustic system development. The second one is passive acoustic techniques, which use underwater microphones to detect and classify the echolocation clicks and the whistles of dolphins and porpoises. And by using arrays of these, it's possible to geolocate these clicks in 3D space. This figure shows the 3 small tetrahedrons of hydrophones that were deployed on the Atlantis turbine. If you were on the webinar yesterday, Doug Gillespie talked a little bit about these. Effectively, each mini array of hydrophones provides a 3D bearing to a vocalizing animal. And the intersection point or intersection area provides an estimate of the animal location. And as Doug mentioned yesterday, it's been used extremely successfully to track porpoises past the Atlantis turbine over the last couple of years. So this is a quick schematic of our system. It's affectionately known as the marine mammal HiCUP. The broad design of it's a seabed-mounted platform, similar to the previous 2 talks. And the aim is to have it deployed approximately 30 meters to the side of a turbine. And it's connected, or it will hopefully be connected by an umbilical cable to a port on the turbine to receive power. The system also uses fibers in the turbine export cable to relay data to shore-based computers in real time. And very broadly speaking, some of the advantages that we see of being connected to the turbine are, in theory, you can deploy for relatively long periods without needing to retrieve and charge batteries. You can, in theory, get data back in real time, so you have excellent data security. And you can also modify data collection protocols or classification and detection algorithms as you go along, and you can process and analyze the data as it comes in. Some of the disadvantages, however, are that it can be logistically highly complex. You're less dependent, being reliable on turbine engineering and operations, and of course, if something goes wrong with the provision of power from the turbine, your system is effectively redundant. So our platform has 2 multi-beam sonars oriented in the horizontal plane, pointing towards the turbine. These are offset vertically by around 15 degrees, and they aim to provide high-resolution XY tracks of animals passing the turbine, and some measure of depth based on the ratio of intensity of the targets between the 2 sonars. You can just about see in our sonar images here, and here is a detection of a harbour seal. And you can see by comparing the intensities between these 2 sonars, you get a measure of the depth, the relative depth within this sonar space. Secondly, underneath this little polyethylene cowling here, we have a series of 4 hydrophones. The other thing I should mention, actually, just before I go into the hydrophones, the two Gemini sonars are mounted on a custom-designed pitch and roll system. And this is actually critical for allowing us to turn 3D tracks in sonar space into 3D tracks in turbine space, and effectively geolocating animals with respect to the turbine. So as I said, there's a single cluster of 4 hydrophones, very similar to the ones that we deployed on the Atlantis turbine in the previous 2 years. And these then provide 2 things. First of all, they provide data to assist in the species classification. So is the target we're seeing on the sonars a porpoise, dolphin, or a seal? They also provide a single 3D bearing which can be matched to the sonar tracks, providing further information on the depth of the animal as it moves the turbine. And there's also scope for adding other sensors such as ABCPs, other sonars, or perhaps daisy chaining platforms if there's a requirement to have more than one platform deployed. And there's a number of publications now which we've put out which describe the general approaches we've taken to detecting and tracking marine mammals using both the active and passive systems. So as both Doug mentioned yesterday and Benjamin mentioned in the previous talk, back in 2017 we had our first attempt at deploying a platform alongside the operational turbine. We deployed a sort of Mark I system alongside the Atlantis AR1500 turbine. And unfortunately, as Benjamin mentioned, some of those disadvantages of the cable system I mentioned became all too real for us, and a power mismatch in the turbine systems meant that we never received power to our platform. And over the 2 years it was underwater, we also had significant biological growth on the platform, and we had some connector corrosion which led to water ingress. So the new designs look to try and consider some of those important lessons we learned from this previous attempt, and both the successes and the failures of this and other platforms. So for the last 2 years, we've been carrying out a series of field tests of the combined sensor systems, tracking animals, working out optimal hydrophone spacing, working out optimal hydrophone locations relative to the sonars, developing detectors and classifiers for both the active and passive data, and try to integrate the sonar and hydrophone data together. And as many of the speakers yesterday highlighted from their studies, close encounters of marine mammals with turbines are likely to be relatively rare events. So persistent long-term monitoring in the order of many months to years is likely to be needed to capture and understand these events. And from this effect, we've been long-term tank testing the sensors to ensure system stability, and that we can effectively synchronize the data from both the active and the passive sensors over periods of weeks and months. And we're currently at the final construction and testing phase. I've just added this little video of the pitch and roll system that we've built being tested in the lab. So just as important as the hardware development is the analysis and data storage software. And as I mentioned, we hope to make as much of the system as possible open access. And to that end, we're using the software package PAMGuard, which is an open source software package that was originally built by Doug Gillespie, and both Doug and Mike Oswald maintain this. It was originally built to provide infrastructure for acoustic detection, localization, and classification of marine mammals. It's therefore well set up to store and analyze the data from the hydrophones. But over the last year or so, Doug and Mike have been further adapting it for the project to include a watchdog system for autonomous monitoring and to incorporate the detection data from the multi-beam sonars. It's also been adapted to automate some of the data archiving steps that we need for both the sonar and the hydrophone data. And overall, this means that the data from the 2 sensor systems can be stored in a common database, which we hope will make the analysis of species classification and the movements far more efficient. And here's a quick example of the kind of tracking data that we get from the combined system. The plot on the right shows a summary data from the sonar and from the hydrophone localizations. The blue dots show the track of a harbour porpoise, starting off about 40 meters from the sonar, heading slowly in towards the sonar. And the lines that you can see flashing up in and out represent bearings, echolocation click detections from the hydrophone clusters. And each of these are color-coded to show the vertical angle of the detection. A couple of things to notice. We do have some good overlap on occasion with the XY plot from the sonar with the bearings from the hydrophone clusters. However, we do have gaps in the clicks. and this is effectively when the animal is eclocating and when they stop eclocating. And this is one of the key problems we had with tracking using the passive data only over the previous 2 years. Another thing to notice is that there's a lot of bearings that don't match up with our porpoise that we're getting on the sonar. This is probably two things. It's probably from other porpoises in a group. There was about 10 porpoises in this group that we tracked. And also, there's potentially a lot of false detections in here. This is before we've had a chance to clean up the hydrocone data. But I hope it gives you a feel for the kind of dual data streams that we're getting coming in and how we're planning to integrate both the active and the passive data. So this is a slide from Fraser at Atlantis. The next steps are to complete the final testing and hopefully deploy the platform alongside one of the operational turbines in the Magen array. And this slide describes some of the broad design principles of the integration of the platform into the Magen turbine systems. And critically for us, the new approach is to plug the platform into this rather neat subsea hub, which Magen have had built, in part to allow the connection of environmental monitoring systems. And importantly for us, it allows us the flexibility of being able to plug the system in and test it on a ship prior to deployment, and it allows us to subsequently retrieve the platform if necessary at a later date. And this, both the hub and the platform are due for deployment towards the end of this year. Now, at this stage, we're still looking at monitoring movements of individual animals around individual turbines, but as Beth sort of highlighted in the last talk, hopefully we can start to expand this out to array-scale monitoring. And we're actively starting to think about some of the best approaches we might take to measuring marine mammal responses at the kinds of scale envisaged for the industry, the kind of tens to hundreds of turbine scale. But in the meantime, hopefully we can collect some more data like this later in the year, start to add tracks of animals, particularly seals, in close vicinity to an operational turbine, and start to reduce some of that uncertainty of mammal interactions with turbines. Thanks very much.
Well, thank you very much for inviting me to partake in today's webinar. I'm going to talk today about the Fundy Advanced Sensor Technology program that FORCE implemented a number of years ago now. It consists of a series of both onshore and subsea instrument platforms to be involved in site characterization and a series of other activities for environmental monitoring that FORCE undertakes at the FORCE site as well as with its partners elsewhere in the province. This has been an ongoing project for a number of years. It was actually started well before I began with FORCE. It has a number of participants dating back a long time ago as well as several funding sources. Oops. So just to provide you with some context, FORCE is a not-for-profit organization that was established in 2009 to serve as a hub for in-stream tidal power development and research in Canada, as well as to determine whether or not in-stream tidal can be a part of Canada's marine renewable energy future. But we have two mandates that FORCE fills. First, we serve as host by providing infrastructure, both onshore and offshore, to tidal power developers to assist in testing tidal technology. We also have a stewardship role to play where we conduct environmental monitoring for a variety of different ecological components of our region, as well as research and engagement activities. And today, FORCE is Canada's leading research center for the demonstration and evaluation of in-stream tidal energy technology. So as I mentioned at the beginning, the FAST program consists of a series of onshore assets as well as subsea instrument platforms. This is used in combination for advancing site characterization for tidal power developers, establishing environmental monitoring standards and technologies, as well as for developing marine operational capabilities. Just briefly, our onshore assets include things like X-band marine radar for characterizing waves, surface currents, as well as for modeling hydrodynamics and oceanographic currents. A weather station, which provides high-resolution imagery, and it's web-enabled, as well as a tide gauge that provides real-time web-enabled data that is available on FORCE's website. What we're really here to talk about is a series of subsea platforms that FORCE has that it uses in environmental monitoring and site characterization. The largest of these is FAST-1, which is one of our autonomous platforms. It houses an instrument called the Vectron, which has, at the edges of the cages there, you'll see there are ADCPs, and they're all pointing inwards and upwards at an angle that allows us to measure turbulence in the mid-water column, and this is beneficial for tidal power developers coming to our site. We also have a smaller version platform referred to as FAST-2, which is also autonomous and used for site characterization. In the past, we've kitted this out with ADCPs, CTDs, as well as dissolved oxygen sensors. It's also included instruments like fish tag receivers, subsea cameras, and lights for illumination. This platform is FAST EMS. It is a cabled platform intended to provide real-time data. It's not as far advanced as the AMP platform or the flowback system that Benjamin spoke about. It remains a research and development project. There were some initial problems with the MUX and some fiber optic connections that are still being worked out. It contains a series of directional sensors as well as ADCP. It's been kitted out with a multi-beam imaging sonar with a dynamic pan-tilt unit so that when this platform is deployed, if it's not in the exact positioning we want it, we can adjust the field of view for the Gemini imaging sonar. It also houses a subsea camera, a Sculpin, a series of IC-listen hydrophones for PAM monitoring, as well as a multiplexer and a termination canister. We deployed this in 2018 in the intertidal zone of FORCE for an initial assessment of Gemini performance, as well as the CTEC tracking software capabilities. And that report is available through me. If you want to email me, I'm happy to provide this. This was something written by Haley Vyman. We also have another platform, FAST-3, which is autonomous. It's used for a variety of different projects, and it's flexible in the sense that it exists as a frame that can be outfitted with a variety of different sensors depending on what the monitoring objectives are. One of the ways that we've used the FAST-3 frame was for a comparative assessment of echo sounder capabilities. So we worked collaboratively with Haley Vyman and Acadia University here in Nova Scotia to combine FORCE's mobile hydroacoustic surveys using a downward-facing EK80 with an upward-facing WBAT on the platform to resolve some of the issues around variability in fish distributions at the FORCE site and to help determine an optimal monitoring approach. FORCE does a series of mobile survey transects over the FORCE site in a reference area, and the platform was deployed alongside one of these transects. And there were a series of multiple deployments where we could compare the data over multiple months and seasons. Generally what was found was there was a strong effect of tide and diel stage on fish density estimates, with greater variation being observed over short time frames and over the course of the year. And this really drove home the point that to understand what's going on in a highly dynamic marine environment like the Minas Passage, we need more or less continuous data collection because it allows the diel and the tidal variability to be quantified and then isolated from the longer-term trends in fish density and distribution that we need to understand for assessing effects of tidal turbines on fish. The FAST platform is also being used in the Pathway program, which you might have heard of before. It's a program to establish a regulator-approved integrated monitoring system that helps to support environmental permitting for tidal power developers. The platform is primarily used in the third phase of the program, which involves a series of experiments to validate different technology performances in high flow environments. And here we're using a staged approach to test sensor utility in high flow environments. It's being used in a series of experiments to assess performance of different passive acoustic monitoring technologies, relative performance of echo sounders in different configurations, as well as imaging sonars, and then ultimately being used for integrating the variety of different sensors onto the platform itself. One of the experiments that we used the FAST-3 platform recently for was a comparative PAM assessment. And here we had identified 5 different PAM technologies that we were going to co-locate on the platform and assess. So we had a C-pod, an F-pod, an AMR G4, so it had 4 different hydrophones and different shrouds, a sound trap, and an IC listen. And these were all deployed in July and again in September. And we conducted a series of passive drifts using an IC talk to emit synthetic harbor porpoise clicks over a range of different tidal conditions over the forest site. Now, the data is currently being analyzed, but the preliminary results suggest that the IC listen was the most sensitive in terms of detecting the clicks over the broadest range of tidal conditions. But we did detect an elevated level of false positive detections, and so we're now turning our attention towards developing a new detector and classifier algorithm that can filter out those false positive detections so that we can have a robust hydrophone system as we move forward with the Pathway program. Another experiment that the FAST-3 platform was used with recently was in collaboration with Sustainable Marine Energy Canada in Grand Passage, Nova Scotia, where they have deployed their Plathi floating platform tidal energy device. And here the question was, where should we be deploying hydrophones for effective monitoring of harbor porpoise? Should they be on the bottom? Should they be suspended and mounted from the platform, the tidal energy platform itself? And so we did a trial run in fall 2019, again, where we had an IC listen mounted to the platform and deployed on the seabed, and then the same device mounted on the Plathi itself about 1.5 meters below the water. And we conducted a series of passive drifts, again, with an IC talk to understand relative performance and whether or not turbulence and entrained air influences the ability to detect those signals. And here are some early results from that trial run. On the left, you have the IC talk signals being very clearly detected in the spectrograms from the bottom-mounted hydrophone. However, we did detect some level of electrical interference, not uncommon for tidal power developers, when the hydrophone was mounted on the Plathi itself. And we suspect this stems from the hydrophone being integrated into a power inverter that could have caused this interference. Now, another series of experiments we're working on deals with assessing echo sounders using the FAST platform. So here, the objective was to investigate target detection capabilities in both surface and bottom deployments. So the first experiment involved co-registering targets using an upward-facing WBAT deployed on the seabed, and then looking to see with an optical camera whether or not those targets could be detected. The data phase for this has been completed. We've got the experiment conducted, and we're in the process now of analyzing the data. Just to give you some perspective on the series of conditions we're seeing in Grand Passage, we see the full range of conditions you might expect for a high-flow environment. Echograms during slack water periods with lots of potential fish targets distributed throughout the water column, but then in any serious degree of flow, more or less entrained air scattered throughout the water column. Now, this has presented a bit of a challenge, as you can anticipate, but some of the echograms are just terrible and are just removed entirely from the analysis, limiting the number of usable echograms for analysis. The second experiment involves the deployment of the WBAT again on the bottom, looking upwards, and this time using the camera, but also a Gemini imaging sonar, again to co-register any fish targets in the water column. The data collection phase for this has been completed, and we're now in the process of processing the data and conducting analysis. And then the third experiment, which will be executed later this spring, involves a comparison of the upward-looking WBAT versus the downward-looking EK80. And again, this is to understand whether or not entrained air in the water column and the potential for signal scattering impacts our ability to detect targets and to inform us as to whether or not we should be deploying echo sounders from a subsea platform moving forward, or whether or not we can effectively monitor by having a echo sounder looking downwards and deployed from the plant height itself. So I just wanted to thank you very much for listening, and if you've seen my talks before, I often include this slide just to drive home the point that we really need to continue on with broad-scale collaborations as we move towards our common goals of marine renewable energy generation, but also a healthy marine environment. Thank you.
Thank you, Dan. That was just great. So we have a number of questions that have come in. Some of them are from multiple speakers. Let's just sort these a little bit. A question that's for Dan, but also for James, so might want to take it in sequence. The sensor platforms as presented are a great addition to environmental monitoring. Thank you. Progression and improvement of these platforms was well described. Can you describe what you see as the next step of this improvement? Is it likely to be a hardware or software related, short term like 2 years, or longer term 5 years plus? Thank you. So Dan, do you want to address that, and then maybe James?
Yeah, sure. I don't think that it's one or the other. I think it's both. I think it's important to remember that what we've done here is to take a series of sensors that are intended for more benign marine environments and have asked them to perform in incredibly challenging areas. I think there is both an engineering feat that needs to be accomplished, which is being accomplished by James Jocelyn and Benjamin Williamson and others. But there's also the other aspect, which is to advance the data processing and the automation component of this to provide regulators and the broader scientific community with environmental monitoring results and research on a timely manner.
Great. James, some thoughts?
I would echo what Dan is saying, that it's both hardware and software development is still needed. That for our system and our group, we are now focusing more on the software as I think the main piece of hardware that really has needed to be developed was this ability to integrate the instruments into a single package, which it's a lot more complex than at first it appears, because you need to be able to basically synchronize all of the instruments and get them to all work together as opposed to against each other, which is often the case, especially with active acoustics. But on the software side, I think there's still a big need to collect more data and use that data to drive the software development of these robust target detection and classification algorithms. And we are really just scratching the surface on what is possible with this data once you actually start getting these data streams. To date, basically, all of the data that we have collected has really been used to design the software, as opposed to really analyze the data and get good information out of it. And the type of information we are getting is very superficial, and I think there's a lot more that you can dive into on that. So that's where we're starting to turn our attention with the next upcoming deployments that we have. And I guess I would say that in the next couple of years, there's a lot of development that can happen there, but then it's something that needs to be implemented over a much longer period of time to really answer these questions to the point where we are retiring risk around marine energy devices.
Great, thanks. Gordon, do you have any thoughts on that? Gordon or Doug?
I would agree with most of the things people have said there. I think the one thing for me is that I think we really need to get these things deployed beside operational turbines. And there's going to be things that come up with the analysis of data once we're in place that I think we're going to have to focus on over the next few years. Challenges in terms of once the data starts coming in terms of movements of animals. What are the sort of unforeseen challenges that we haven't thought of? And I think we sort of almost have to focus, some of the analysis efforts and the software efforts in that side of things once the data start coming in.
Oh, great. Benjamin and Beth, what about your plans? Where do you think we're going?
I would agree that the current focus is on the software. I think for the hardware, it's reassuring to see that the field is converging on a fairly similar instrumentation suite for different receptors. And at the end of the day, with the instrumentation, we're limited by physics. We're operating these instruments in challenging conditions. So I think the hardware we've proven is reliable. We can collect these data sets. And I would say maybe like Gordon says, it's a limited opportunity to better build up the training data sets with the deployments we've had so far to see how well do these systems work under different conditions, how representative is one site of the other, how transferable are the results. Beth, would you add anything to that?
Yeah, those are all excellent points. I think the only thing we do need to be thinking about the array stage, and it's going to come faster than we think. So I think starting to think up in terms of scale is the next question as well.
Great point. Doug, did you want to add something to that? So maybe here's a question that maybe focusing on Benjamin and Beth, your presentation. Obviously, being able to relate the biology to the physics is really wonderful, the physics of water movement, but it's really hard to do with reasonable accuracy, particularly at the modeling level, because the hydrodynamic modeling is so detailed that the biology is hard to catch up. Can you talk a little bit about where you think we're going with that and what your expectations are?
I might pass that one to Beth, actually. I'm happy to have a go, but with Beth and with the PhD students we have, and Beth, with your ongoing work in SuperGen about modeling across scales, I think that's an active area of research, isn't it?
It is, and indeed, of course, none of that is easy, but anybody who's been to a tidal site and stood there for any length of time will see that the different species are using quite different bits and parts of the water column. And the lovely thing about those areas is the physics is so strong there, you actually don't need your instruments to delimitate where the shear is and where the boils are. And so in the smaller areas where we've been able to do vantage points, it's quite clear that species are using the physics. And actually, I do encourage you to go see Anna Kuto's talk online. We are getting to the point where, because we've got data every 3 seconds on our surveys, and we've got instantaneous data on the animal behavior, we are getting to the point to get some models that are quite decent in predicting which species are where.
Great, thank you. Sticking with Beth and Benjamin one more time, we have a question about are you using our hydrodynamic model to simulate the distribution of prey, and if so, are you focusing on plankton or adult fish or other?
We've got several different ways we are looking at that. In our very large scale, we use species like herring and sand eels, but mostly the main prey species. And there's some quite complex spatial modeling with our 3D models. And if anybody's interested, they can email me and I can send them a bunch of references. On the finer scale stuff, like I say, with the EK60 data from the ships, the downward facing, we were able to split our species into at least fish species of swim-bladdered fish species versus fish species without swim bladders, i.e. sand eels. So we're at least able to do that so far in the site, and it's really quite interesting that those types of fishes are in very different areas and have very different predictability with the hydrodynamics.
Great, thank you. So we have a question here that I'd like to pose to all the panelists, which is at a little bit the higher level, almost, not quite philosophical, but almost. We know that ocean heating and acidification related to CO2 emissions are the overriding threat to marine life. Why is this not factored into our environmental assessments, or how can we factor into this into our environmental assessments for looking at risks from marine renewable development? Anyone like to address that? Or argue with the premise, either one.
If nobody else comes in, I feel I've talked a bit, but I've definitely, our group is working on that as well, where we're trying to look at the effects of climate change, and climate change, the fact that renewables will reduce our use of CO2, have that in the equation for environmental impacts and cumulative impact assessments. But unfortunately, most regulators and the way the system is set up for impact assessments, you cannot have positive impacts like that brought into the equation. Plus, it's very hard, local versus global. You may, all of these things may bring down CO2, but you've still got a local effect of the potential effect on your biological population. So it's a tricky question, but it really should be on the agenda.
That's a great answer, Beth, and I tend to think in terms of turning to our legal colleagues and getting them to begin to challenge the premise in a number of countries. Why are we not taking these into account? I agree. Anyone else like to address that one? It is a bit of a hot potato. So we have a couple of other questions here for James. Along the lines of your long-term plans for the AMP, will the information for producing the AMP become open source?
Andrea, yes, for the most part. There's a number of publications that are out there already and that we are currently working on that describe the system development, as well as the methods for the target detection and tracking in the software. At the same time, I think it is hard to emphasize the complexities of operating this type of a system and the complexities of getting the data, the right data out of the system when you are using it. So we are also working to, in a way, commercialize the system, really just offer this type of deployment and data processing as a service so that we can help people along those lines. So I think there's need to get this type of design and development out there so other people can be using it when they're able to, but we also need to acknowledge that not everybody is going to be able to operate one of these systems or build their own. So there needs to be more options out there for people who basically just want to get at this type of data from a deployment.
Great, thank you. Another question that I think goes to all the panelists. When we think about the technology we're using in looking for marine life around these turbines and WECs, which of the technologies do we think is the least, has the least impact on marine life, and how do we deal with the fact that some of our detection methods do have impacts? Anyone like to address that?
This is James. I'd like to talk about at least how we deal with the fact that some of our detection methods have impacts. I think that's a really important thing to keep in mind when designing a study. Things like lights and echo sounders and some active acoustics can have a direct impact on the behavior of the animals you're trying to monitor. And so basically you need to be using these in a way that is strategic and only use them when they are getting you the data that is helpful. So this is, with the AMP system, this is how we've basically been trying to use lower bandwidth instruments and instruments that have a lower impact to trigger the, like for our system, the camera and lights basically only turn on the lights at night if you know that there is a target in the field of view that you're trying to capture an image of. And otherwise just keep them off, and only do so for a short period of time as well. And similar for our echo sounder, we basically will turn it off if we know that there is a species that present that can hear it. So I think those are both important factors.
so that the active acoustics are the ones we're more concerned about in terms of affecting sea life on an ongoing basis. Anyone else like to address that about effects of our observations on sea life?
Maybe I could jump in. It's Gordon here. But I think the thing for me, it's great to hear James say that. I mean, it's certainly it's been considered much more, over the last few years in terms of potential effects of some of the sensors. And I think, particularly in terms of trying to measure responses to turbines, I think the important thing is that your system that you're using doesn't mean that you conflate responses to your sensor system to responses to your turbine. And certainly more and more information coming out, particularly in terms of the active acoustic side of things, in terms of which species are likely to be able to hear different active sonars. So in terms of tailoring your sensor system to particular species, I think that there's more and more information out there to allow you to do that in an environmentally sensitive manner.
Great. Dan or Benjamin, Beth, any other thoughts?
It's Benjamin here. I would agree completely. I mean, more and more of these sensors are being characterized. I'm aware Gordon's done extensive work with the multi-beam echo sounders. Emma Cotter put out a publication in 2019 in Marine Pollution Bulletin for acoustic characterization of some of the commonly used sensors on these platforms. So with that information, it will give you an idea of what ranges are these systems likely to be audible. You can then match up to what receptors, what animals, what species you're interested in monitoring. But I guess the other point is audibility in these very, very noisy sites already doesn't necessarily cause either an avert or a physiological behavioral response. And for that, until we have observation with multiple sensors, we don't know. We're speculating. So the cautious approach, of course, is to avoid audibility, and we're getting more information on that.
Great. Dan, any thoughts? And maybe as you answer, here's the sort of follow-up to that question. What if continuous monitoring is being required by regulators? How do you get around the turning on, turning off, and still maintaining what is effectively a continuous record?
So, yeah, I've thought a little bit about this, and I think what it comes down to is speaking with the regulator and talking to them about representative sampling. If you have a instrument platform that's got a combination of active and passive acoustic instruments on it, obviously you have to set up some sort of duty cycle. And if you were to understand how frequently or the abundance of targets or distribution of the water column over a longer period of time, if you could, through statistical means, understand how frequently you need to sample to be representative in your sampling to still convey the relevant information, I think that is a strategic approach for setting up appropriate monitoring moving forward.
Great. So I think we are about done here today. I just want to thank everyone for being here, let you know that we will be, we have recorded this session, including the questions and answers, and we will be posting those after we check with the presenters, of course. We also hope to hold another of these forums sometime in the next 2 to 6 months, depending on the interest level. And we'd really appreciate any input on topics of interest you'd really like to see us drill into more, and suggested speakers, of course. And I think we just touched on a couple of things towards the end there, is how do we go about developing appropriate monitoring programs that allow us to collect the information necessary to support consenting or permitting, at the same time not disturbing the animals and not necessarily having to take 24/7 monitoring, which is difficult with many of these packages. So if you have thoughts you want to add to the chat box, that's great. Otherwise, over the next while, if you want to send any input to Dori Overhoos, we will compile those and help to form our next forum. Thank you very much, and I think we'll conclude.